Hello guys, welcome to my channel. In today's video, we will walk through another example problems in determining the strength of a steel column. So the problem is determine the LRFD design strength and the AISC allowable strength for the column shown in figure below. So if the 50 KSI steel is used and using the column critical stress value in Table 4-22 of the AISC manual. So here, as you can see in the figure below, here, the height of the column is 15 feet and the top support condition is pin and the lower end is fixed. So we are using here W12 by 72 steel column profile. Now, before we proceed guys to the solution, I would like to share with you regarding the application, how this kind of column conditions applied in the actual design or site. So we have a similar condition this based on our from our previous project, and let me share with you guys very quick. So here we have an existing floor framing plan. It's a concrete flooring with a deep beam here. The length of the beam is 11.25 meters or equivalent to 37 feet. So actually the clients are proposing to change the purpose of this area where the live load is almost doubled from previously considered in the design. So we found out based on our investigation that this beam from here to there could no longer handle the additional imposed load. So we propose to provide steel columns W12 by 65 at the middle of the beam to carry this additional load. So the beam, the column is fixed at the soffit of the existing concrete beam by means of healthy method, and the lower end is we have the base plate and anchored to the existing wrap foundation. So the solution, actually the calculation of this column is very similar to the problem that we are going to solve right now. So back to the problem guys. So here, so let's proceed to the solution. The section properties of these columns for 12 by 17 steel. So we have this area, we have the radius of gyration along x-axis, and we have the RY, which is 3.04, the depth 12.3 inches, the width of the beam is 12, and we have the plan's thickness, the weave thickness, and we have also the key value here. So first of all, we need to check the slenderness of the flanges. So we have to repair the table B4.1 A. So in table B4.1 A, let us check. So in this table, we have compression element subject member subject to axial compression, and the other side is compression element member subject to flexure. So we don't have to confuse with this one, because this one is for bending flexure. So in our case, for the columns unsteepened element, we have the condition for width to thickness ratio B/T, which is this one here. B/T should not be greater than this limiting width to thickness ratio of slenderness requirements, which is 0.56 the square root of E/Fy. So this is for the flanges and steepened element. The purpose of this guy basically is for the local buckling when the column is subject for compression. Now for the weave element, we have the depth to width thickness ratio, and also the limiting ratio for the slenderness is 1.49. We are using this profile actually. 1.49 to the square root of A over Fy. So this is the table where we have that equation actually in our solution. So going back to our problem solution. So for the slenderness, we have B over T 12 divided by 2, half of the width of the beam divided by 0.67, which is the flange thickness. Flange thickness is, let me check. Okay, 0.67 is equal to 8.996. And for this should be less than to 0.56 square root of A over Fy, which is 0.56 square root of 29,000 over 50 KSI equal to 13.949. So which means since this is less than to the limiting width thickness ratio of the slenderness requirements, so our flanges is not non-slender unsteepened flange element. So the next one is the slenderness of the weave. We need to check the depth to width thickness ratio. So we have this equation D minus 2K over TW is equal to 12.3 minus 2 times 1.27 for that is key, all over 0.43. That is the weave thickness, which is it will give us 22.7, which is less than to 1.49 square root of 29,000 over 50. That is equal to 35.88. So which means our weave is non-slender. So we are okay for local buckling requirements. So the next one is to determine the strength of the columns. So we are, since column condition is the other end is pin and the other one is fixed. So we need to use the key value, which is we are on this condition, pin fixed. So this is from table C-E-7.1. So we use this 0.8. See here, this one. We use that 0.8. So back to our solution. KL over R, because this is the governing one, it will give us a big value for KL over R. Then we need to check this figure from the this value from the table. If we check the table here, table 4-22. So table -22, we have the strength of steel 36, we have 42, but our steel is, we are using 50. We are using 50, so we are in this column here. And the KL over R value in our case is 47.37. So we are in here 47, in between of 47, 48. So we need to interpolate this value here for FCR over omega and the LRFD value. So to interpolate this, I have calculated for this value by interpolation. So we have 38.19 25.43. That is for ASD, and this one LRFD according to this. So that is guys for the table 4-22 using this one here. So this is the value for our LRFD, which is this one here from the table. Then we have to multiply that by area. So we have the strength, compression strength of 805.8. And for the ASD, P over P sub N over omega, we have this one. That value is 25.43 from here. We have already interpolated that value earlier. Then times the area of the steel, gross area. So we will have 536.6. So this is our governing load of the column. So guys, if you find this video helpful, please don't forget to like or subscribe so that we can still share this video to other engineers. And thank you for watching, and see you next time. Bye bye.